tunnels. I will show you the fourth one. And this is what I found out, that as we look at the Sphinx.
For over a century, the Great Sphinx of Giza has sat in the desert with its face fixed toward the sunrise, and almost everyone who has ever written about it agreed on one thing. It was carved around 2500 BC, on the orders of a pharaoh named Khafre. Then a handful of geologists looked closer at the walls of the trench surrounding it, the deep enclosure cut into the bedrock to free the statue from the plateau, and they found something that didn't fit. Not scratches from wind, not the pitting salt leaves behind, long, rounded vertical grooves, the exact signature water leaves when it runs down stone for centuries. And Egypt's Giza Plateau hasn't had centuries of rain like that in over 4,000 years. If those marks really were carved by water, the math only works one way. The Sphinx would have to be standing there thousands of years before the pharaoh most textbooks credit with building it. This is where an old, unresolved argument in geology meets a strange new twist. It just got run through an AI with no career, no tenure, and no textbook to protect. And the analysis didn't just confirm one side of a decades-old argument. It found something in the proportions of the statue itself that almost nobody had thought to measure carefully before. What the official story actually says. Before getting into what's disputed, it's worth being precise about what the mainstream account actually claims, because the debate only makes sense once you understand exactly what it's arguing against. The Great Sphinx sits on Egypt's Giza Plateau, carved from a single continuous mass of limestone bedrock rather than assembled from separate blocks. It has the body of a lion and a human face, and that face looks directly east, toward the rising sun. According to the standard chronology, the Sphinx was carved around 2500 BC, during Egypt's fourth dynasty, on the orders of the pharaoh Khafre. Many Egyptologists believe the face was carved to resemble Khafre himself, and that the lion's body was chosen to symbolize royal power and protection. The origin story is almost architecturally tidy. While workers were quarrying limestone blocks to build Khafre's pyramid nearby, a large outcropping of lower-quality stone was left behind in the quarry pit. Rather than waste it, that leftover mass was carved in place into a colossal guardian figure for the pyramid complex. This chronology isn't a guess pulled from nowhere. The Sphinx sits directly beside Khafre's pyramid and causeway. Its stylistic details line up with other confirmed Fourth Dynasty architecture, and no direct archaeological evidence, no inscription, no independently dated artifact has ever surfaced that overturns it outright. That combination of proximity, stylistic consistency, and absence of a contradicting smoking gun is exactly why this remains the position taught in universities and printed in textbooks worldwide. Any serious challenge to it has to explain away all three of those pillars, not just one. It's also worth understanding just how physically demanding the accepted construction story actually is, because the scale involved is part of why the standard chronology has held up as well as it has. The Sphinx measures roughly 240 feet long and 66 feet tall, carved almost entirely from a single continuous limestone outcropping rather than assembled piece by piece. Ancient Egyptian workers using copper chisels, stone hammers, and wooden tools are believed to have spent years shaping that mass of rock into its final form, coordinating labor at a scale that required serious social organization. Skilled stoneworkers, engineers capable of managing proportion and structure at that size, and a workforce large enough to move the excavated debris away from the site entirely. Fourth Dynasty Egypt, with its centralized administration and its proven ability to build the Great Pyramid itself just a few hundred meters away, was demonstrably capable of a project like this. That capability is part of the argument for Khafre's authorship. Not just that it's plausible he built it, but that the civilization around him had exactly the organizational infrastructure such an undertaking would require, where the doubt actually started. The challenge didn't come from an amateur theory or a documentary looking for a dramatic angle. It came from geologists doing exactly what geologists do, reading the rock. When they examined the walls of the enclosure trench, cut around the Sphinx's body, the surface told a story that didn't match its supposed age. The grooves cut into the limestone weren't straight scratches. They were deep, rounded, and undulating, running vertically down the trench walls in a pattern geologists describe as wave-like. That distinction matters more than it sounds like it should, because different erosive forces leave genuinely different signatures on stone. The same way a knife cut looks different from a burn mark. Wind-driven sand tends to erode limestone horizontally, and it wears down lower sections of exposed rock more aggressively than upper sections, since that's where the heaviest, most abrasive sand grains travel. Salt weathering, which happens when crystals form inside the stone's pores and physically force it apart, tends to produce pitting and flaking distributed unevenly across the surface, not long continuous vertical channels. What geologists were looking at on the Sphinx's enclosure walls didn't cleanly match either pattern. It matched something else: the specific vertical rounded profile that forms when large volumes of water repeatedly sheet down a stone surface over a very long period of time. And that observation ran headlong into a geological fact nobody disputes. Today's Sahara is bone dry. But it wasn't always this way. Climate scientists have firmly established that the region went through what's known as the African humid period, a stretch lasting roughly from 14,500 to 5,000 years ago, when much of North Africa, including the area now covered by the Sahara, was green, grasslands, lakes, seasonal monsoon rainfall reaching areas that haven't seen meaningful precipitation in millennia since. If the Sphinx's enclosure walls really were carved by sustained rainfall, and if that specific kind of prolonged, heavy rain hadn't fallen on Giza since roughly 3000 BC at the latest, then simple logic forces an uncomfortable conclusion. Whatever the trench was carved around must have already existed while that rain was still falling. Why a few centimeters of stone became an argument about all of human history. This is the point where a fairly narrow geological observation turned into one of the most contentious disputes in modern Egyptology, because the implications reach far past a single monument. If the erosion really is rainfall, and if that rainfall stopped being available in Giza by roughly 3000 BC, that pushes the earliest possible date for the Sphinx's core structure, back thousands of years earlier than the reign of Khafra, potentially into the range of 7000 BC, or considerably earlier, depending on which end of the humid period the carving falls within. And that's the detail that makes mainstream historians dig in hard, because at that point in human prehistory, by every archaeological record currently available, there was no pharaonic Egypt, no hieroglyphic writing system, no centralized state capable of organizing the kind of large-scale stone engineering the Sphinx and its enclosure represent. Most of the archaeological record for that period across the region shows small mobile groups of hunter-gatherers, nothing resembling the labor organization, tool technology, or social hierarchy required to carve a structure this size out of solid bedrock. That's precisely why the geologists' water erosion argument didn't quietly settle into the textbooks the way lesser revisions to Egyptian chronology sometimes do. It would mean either that Egyptology has fundamentally misdated one of its most famous monuments, or that a civilization capable of monumental stone construction existed thousands of years before any other confirmed evidence of one, and then largely vanished from the archaeological record entirely. Mainstream Egyptologists, led prominently by researchers like Mark Lehner, who has spent decades mapping the Giza Plateau in extraordinary detail, have pushed back hard, arguing that the erosion patterns can be explained by other, less exotic mechanisms operating over a much shorter and more conventional time frame, and that a handful of eroded grooves cannot outweigh the site's clear stylistic and archaeological connections to Khafra's Fourth Dynasty complex. The debate has run for over 3 decades now, largely between a small group of geologists on one side and the mainstream archaeological establishment on the other, without ever fully resolving. What happened when the entire case got handed to an AI? That standoff is exactly the situation that led someone to try a different approach, feeding the entire body of evidence, both sides of it, into an AI system with no professional stake in either outcome. The system used was Grok, developed by Elon Musk's XAI, and the appeal wasn't novelty for its own sake. An AI has no tenure to protect, no 30-year body of published work resting on one conclusion being correct, no institutional reputation riding on the answer. It simply processes whatever data it's given and looks for the patterns the data actually supports. The dataset assembled for this analysis was substantial. Laser scan data of the Sphinx and its surrounding enclosure, providing precise, high-resolution measurements of the eroded surfaces. Historical erosion surveys conducted by earlier researchers giving a record of how the rock's condition has been documented and changed over time. Reconstructed ancient climate models for North Africa, mapping out rainfall patterns across the region for the past several millennia. Published scientific literature on exactly how limestone weathers under different conditions, wind abrasion, salt crystallization, and sustained water flow, each producing measurably different surface signatures. Seismic and subsurface survey data collected around the Sphinx over the decades, and a wide set of historical photographs and site measurements taken across more than a century of expeditions. Critically, the system wasn't fed a preferred conclusion. It wasn't told that Khafra's timeline was correct, or that the rainfall theory was correct. It was asked to weigh the competing physical evidence and report what the data actually supported. The scale of that dataset matters, because it's the difference between an AI producing a genuinely useful comparative analysis and an AI simply generating a plausible-sounding narrative. Decades of geological survey work on the Sphinx already existed before this analysis was ever run, going back to the original erosion studies published in the late 1980s and early 1990s. What hadn't existed before was a single unified pass weighing every one of those data sources against every competing hypothesis simultaneously, at a scale and speed no individual research team had ever attempted. That's the actual value proposition here. Not new evidence, but a more exhaustive comparison of evidence that was, in most cases, already sitting in published papers and archived survey reports, scattered across different research groups who often weren't directly engaging with each other's work. What the AI actually found in the stone. The analysis started exactly where the geologists had started decades earlier, with the grooves themselves. Every measurement that had gone into the original debate, groove depth, width, vertical orientation, and curvature, got run through a comparative statistical analysis against the 3 competing erosion mechanisms: wind and sand abrasion, salt weathering, and sustained water flow. According to reporting on the analysis, the result leaned decisively toward one explanation. The erosion pattern matched the water flow signature with roughly 94.7% confidence, a significantly stronger statistical fit than either the wind erosion or salt weathering models produced. That figure doesn't mean the alternative explanations are impossible. Statistical modeling of ancient erosion always carries real uncertainty, and the underlying comparison datasets have their own limitations. What it does mean is that, weighed purely against the available physical evidence, water erosion was the best supported explanation the analysis could produce, not merely one plausible option among equally strong competitors. The system then pushed the question further. Assuming the erosion is genuinely rainfall-driven, how long would it take grooves this deep to form? Cross-referencing established limestone weathering rates against the reconstructed regional rainfall record, the analysis estimated that this level of erosion would require sustained rainfall over a period lasting centuries, not a handful of unusually wet decades, and not a short-term climate fluctuation. If accurate, that timeline points toward the wetter, greener period of Giza's deep past, meaning the Sphinx's core structure would need to have already existed during that window to have been eroded by it at all. The head that doesn't match the body. From there, the analysis turned to something almost every visitor to Giza has noticed without ever thinking too hard about it. The Sphinx's head looks small relative to its body. For decades, that mismatch has generally been chalked up to artistic license, or simply accepted as an unremarkable stylistic quirk of the period. Rather than treating it as an aesthetic footnote, the system measured it directly, comparing the head's proportional volume against the body as a whole, and checking whether that ratio matched what you'd expect if the entire monument had been carved as a single unified design. According to the analysis, the head is meaningfully smaller than the proportions of the rest of the structure would predict. Layered on top of that came a second independent observation. The weathering pattern on the head and neck looks distinctly different from the weathering on the body. The body's erosion signature leans toward long-term water exposure, consistent with the trench walls. The head and neck instead show wear more consistent with wind and wind-blown sand, a dry climate signature. If that distinction holds up, it implies the head and the body were not necessarily exposed to the same environmental conditions for the same span of time, which reopens a long-standing, genuinely fringe hypothesis known as the recarving theory. The idea that the Sphinx's head may have been reshaped at some point significantly later than the body itself was originally carved, possibly recut down from a larger, different original form, conceivably a full lion's head. It's a purely engineering-based argument as much as an archaeological one. Stone can always be carved down to something smaller, but no amount of later carving can make an existing block bigger. A smaller-than-expected head is at least consistent with a later recarving having taken place. It's worth being direct about where this idea stands scientifically. It remains a minority hypothesis with no confirmed archaeological evidence, such as tool marks conclusively dated to a distinct later period, and it is not accepted by the mainstream archaeological community. What the sky says, and why most experts don't buy it. From the stone, the investigation turned toward the sky, following a genuinely famous line of speculation in this field. The Sphinx's face points due east, aligned with the rising sun on the spring equinox, a fact nobody in this debate disputes.